Okay, so the very last section of chapter 2 is section 2.6, rational functions. So the rest of chapter 2, we've been talking about polynomial functions. And the reason that rational functions are thrown in with polynomial functions is because the definition of a rational function is that it's the ratio of two polynomial functions. So the numerator is a polynomial function, the denominator is a polynomial function. Now, we know that a denominator cannot be equal to 0, right? Then the function would be undefined. So for rational functions, we're going to have to exclude those values from the domain that would make the denominator equal to 0. So where polynomials had implicit domains that were all real numbers, rational functions are going to be all real numbers except for those values that would make the denominator equal to 0. Okay. Now, what happens at those domain restrictions? So the values that we need to exclude from the domain, those are going to correspond either to vertical asymptotes or to holes, and we'll talk about what those are in a little bit. Okay, so if we want to find the domain of this rational function, I'm going to first rewrite the function. And we want to know what values of x would make the polynomial in the denominator here, so x squared minus 3x minus 4 equal to 0. So the easiest way to determine those values that we're going to need to exclude from the domain is going to be to factor the denominator. So the denominator, it looks like we'll factor to x minus 4, x plus 1. So we can see that x cannot be equal to positive 4 or negative 1. So the domain of f in interval notation would be negative infinity to negative 1, union negative 1 to 4, union 4 to positive infinity. So all real numbers except for negative 1 and positive 4. Okay, for this guy, let's switch colors. I'm going to rewrite the function again. Same strategy, let's factor the denominator. So x plus 3x minus 1. So we can see that x cannot be equal to negative 3. That value would make the denominator 0, and x cannot be equal to positive 1. So in interval notation, that'll be negative infinity to negative 3, union negative 3 to 1, union 1 to infinity. Okay, so any real number except for negative 3 or 1 will give you a real output for this function. Okay, so we're going to talk about now what those domain restrictions, what happens graphically at those domain restrictions. So the first type of kind of graphical manifestation we're going to talk about are holes. So if f is a rational function that is not in lowest terms, meaning that there are common factors in the numerator and denominator that you can divide out, okay, those common factors are going to tell you the location of any holes. So let me give you an example. So let's say we have r of x, and I'm going to write r of x already with numerator and denominator in factored form. Let's do like x minus 1 times x plus 1 over x minus 1. Okay, so this would have been x squared minus 1 over x minus 1. Well, we can see that the domain is going to be all real numbers except for positive 1. Positive 1 would make the denominator equal to 0. If we tried to substitute positive 1 in to r of x, we would end up with 0 over 0. Okay? 0 over 0 is what we call an indeterminate form. And you'll talk more about indeterminate forms next year in calculus. But when we end up with 0 over 0, that tells us, like if we're evaluating a rational function at a specific value and you end up with 0 over 0, that tells you that there is a common factor in the numerator and denominator that's causing that 0 over 0. So in this case, that would be the factor x minus 1, right? X minus 1 divided by x minus 1 will cancel, leaving us with x plus 1. So 1 is our domain restriction. X cannot be equal to 1. But what does this graph look like? It's kind of interesting. So the graph of r of x is actually going to look very similar to the line x plus 1. So to the simplified version of the equation. Okay, but at x equals to 1, since 1 is not in the domain of r of x, there's going to be what we call a hole. And I'm going to represent that hole with an open circle where I would want there to be a point. Graph's not turning out so well, but it has a slope of 1. It's a line with a y-intercept of 1, slope of positive 1, okay? However, we can say there is a hole at, you can say at x equals to 1, or we can also describe, I'm going to be asking you guys to describe the point. So let's just describe the point. At the point 1, 2. And we can see that it's at the point 1, 2 because we just graphed it. But you can actually get the y value that you would want to go with that x value by substituting into the simplified version of the equation. So if we substitute 1 into x plus 1, we get 2. In our previous example up here, right, x minus 1 was also a common factor in the numerator and denominator. So this simplified to be 1 over x plus 3. So actually the graph of f would look like the graph of 1 over x plus 3, and that's 1 over x just shifted to the left 3 units. But there's actually going to be a hole at 1 because x minus 1 is the common factor that canceled. So 1 comma, if I substitute 1 in for x here, so 1 comma 1/4 would be the location of the hole. All right, so let's move on to asymptotes. So asymptotes are lines that the graph of a function approaches, and functions can have two different types of asymptotes. So they can have vertical asymptotes and they can have end behavior asymptotes. And there's actually two different types of end behavior asymptotes. So you can have horizontal asymptotes, or one type of end behavior asymptote, and then slant asymptotes. Okay, so we're going to first talk about vertical asymptotes, because vertical asymptotes are what the other domain, the remaining domain restrictions would correspond to graphically. So the line x equals to a is a vertical asymptote for the graph of a function if f of x either increases or decreases without bound as x approaches a from either the left or the right. So let's think about kind of this simplest rational function that you guys know. 1 over x. You guys are very familiar with that graph, so let's go ahead and sketch that. Right, we have the 2 branches. We have 1 branch in quadrant 1, and the other branch in quadrant 3. Okay, and we did mention this, but there is a vertical asymptote. So back in chapter 1, we did mention the fact that there's a vertical asymptote at x equals to 0. But we didn't really talk about what a vertical asymptote was. And I abbreviate vertical asymptote with VA. So there's a vertical asymptote at x equals to 0. And that's because you guys know the domain for f is all real numbers except 0. And as x approaches 0 from the left, remember how we've talked about how mathematicians are lazy? So for things that we say a lot, so for words or phrases that come up a lot, we like to use symbols. So whenever to write as x approaches 0 from the left, I use x approaches as an arrow, 0, and then where there would be an exponent, I'm putting a minus. Okay, so coming from the negative side, from the left. F of x is approaching, reading the graph, it looks like is approaching negative infinity, so decreasing without bound. And then as x approaches 0 from the right, f of x is approaching, looks like positive infinity. Okay, so we have vertical. If you have a vertical, or if a rational function has a vertical asymptote, it means the function is increasing or decreasing without bound as x approaches whatever that value of a is. Okay, so for locating vertical asymptotes, you need to look at the simplified version of your rational function, meaning you need to have already checked that there's no common factors that could cancel, and the common factor would end up corresponding to a hole. That domain restriction would correspond to a hole in the graph. So then if you look at the simplified version of the rational function, then any values that are left that would make the denominator equal to 0 would correspond to vertical asymptotes. All right, so let's look at this function, identify vertical asymptotes. The numerator is already factored because remember we want to check to see if there's any holes first. So let's factor the denominator. So what is that? 2x plus 5, x minus 3. So no common factors, meaning no holes. Okay, there's no holes in this graph. For domain restrictions, you can see that x can't be equal to negative 5/2 and x can't be equal to positive 3. So because we had this function is already simplified as much as it can be, we know there are vertical asymptotes at x equals to negative 5/2 and x equals to 3. Please don't just list them. These are equations of vertical lines, so I need to see the x equals. And then just for fun, we weren't asked for it, but the domain would be negative infinity to negative 5/2 union negative 5/2 to 3 union 3 to positive infinity. And both of those domain restrictions correspond to vertical asymptotes. Okay, let's look at this guy. You can factor an x out of the numerator. The denominator will factor to -4 minus 3. Okay, so we have a common factor in the numerator and denominator here. But remember, you need to think domain restrictions before you do any major simplifying. Same thing as back in like chapter 1 when we were combining functions. So we know the domain is going to be all real numbers except 3 and 4. Okay. But our simplified equation is x over x minus 3. So there's only going to be a vertical asymptote at x equals to positive 3. It's just kind of a bonus. There's a hole at 4, and then if we substitute the 4 into the simplified version, that would be 4 comma 4. All right, end behavior. We have talked about end behavior before, right? We've talked about determining the end behavior of a polynomial function. So when we talk about the end behavior of a function, we are describing the values that the function is approaching as its inputs approach positive or negative infinity. So basically, as x approaches positive or negative infinity, f of x is approaching what? Is that positive infinity, negative infinity, 0, some other real number? To help us out with determining the end behavior of a rational function, it can be helpful to determine the rational function's end behavior model. So I want to take a step back and think about polynomial functions again. Remember how I said for determining the end behavior of a polynomial function, you really just look at the leading term. So the term with the largest exponent, and so you look at that largest exponent, right, the degree of the polynomial, and the leading coefficient. And the reason is, as x gets infinitely large, that leading term is going to dominate all of the other terms. If you think about the terms as being at a tug of war with each other, that largest term, as x gets infinitely large or infinitely small, is going to end up dominating. And the same thing happens with the polynomials in the numerator and denominator of a rational function. So we can really just focus on the leading terms in the numerator and denominator for the rational function. So our end behavior model, which I refer to as the EBM, is the simplified version of the ratio of the leading terms. Simplified. And then you can use your end behavior model as a reference. So the end behavior model is going to simplify to something that you know the end behavior of already, okay? Something that's a lot simpler than the rational function that you're trying to determine the end behavior for. So your rational function will have the same end behavior as the end behavior model. Okay, so now let's talk end behavior asymptotes. So we've already talked vertical asymptotes, and then the other type of asymptote are end behavior asymptotes. So end behavior asymptotes give us a better picture of what's happening to the values of the function as the inputs, so the x values, approach positive or negative infinity. So the end behavior model gives us an idea, like if the function is approaching, say, as x approaches positive infinity, if the function would be approaching positive infinity as well. And the end behavior asymptote would tell us how the function is approaching positive infinity as x approaches infinity. So it just gives us a better picture of the function's end behavior. like what's really happening to the y values as x approaches positive or negative infinity. So like I said before, there's two types of end behavior asymptotes, horizontal asymptotes and slant asymptotes. So rational functions can have at most one horizontal asymptote. There are other types of functions that might have two horizontal asymptotes, so different horizontal asymptotes for different end behaviors, so as x approaches positive versus negative infinity. But for rational functions, you will have at most one horizontal asymptote. You may have no horizontal asymptote. Horizontal asymptotes imply that a function approaches a value as x becomes large in the positive or negative direction. So basically, as x approaches positive or negative infinity, the function would be approaching some number. Let's call it a. Okay, so the graph of the function may cross a horizontal asymptote, just not at the end. So a lot can happen kind of locally, like about the origin. The graph can cross the horizontal asymptote as many times as it needs to. But then if you were to zoom out on the graph, the graph will just look like it approaches the horizontal asymptotes at the ends. Okay, so I should switch that, to f of x will approach b. Okay, that would mean there's a horizontal asymptote at y equals to b. Okay, so the line, horizontal line, right? Y equals to a constant is a horizontal line. The line y equals to b is a horizontal asymptote of the graph of a function if f of x approaches b as x increases or decreases without bound. So basically, as x approaches positive or negative infinity, f of x would approach b, and then therefore there would be a horizontal asymptote at y equals to b. All right, locating horizontal asymptotes. You can also reference the end behavior model of a rational function to help you with locating horizontal asymptotes, but you actually still have to have an understanding of these rules, especially the first two rules on here. So I want you to understand them, but also it's going to be helpful to just memorize these rules. So if we have a rational function, okay, right, a ratio of two polynomials, the degree of the numerator we're going to call n, and then the degree of the denominator will be m. So if the degree of the numerator is less than the degree of the denominator, then the x-axis, or the horizontal line y equals to 0, will be the horizontal asymptote. And that's because if the degree of the denominator is larger than the degree of the numerator, as x gets infinitely large or infinitely small, the denominator is going to grow at a faster rate or decrease at a faster rate than the numerator, and therefore the function will end up approaching 0. When the degree of the numerator equals to the degree of the denominator, so when n equals to m, okay, remember how I said the leading coefficient, or sorry, the leading terms are our end behavior model, the ratio. Well, if the degree are the same in the numerator and denominator, those x terms are going to cancel, right? If you have x squared over x squared, the x squareds would cancel, or x cubed over x cubes would cancel, leaving you with just the ratio of the leading coefficients. So if the degree of the numerator and denominator are equal, the horizontal asymptote is going to be at y equals the ratio of the leading coefficients. Okay? And then the third case, there's no horizontal asymptote at all. So if the degree of the numerator is greater than the degree of the denominator, okay, that means that the numerator would be increasing at a faster rate. And there's actually not going to be any horizontal asymptote because the function would be approaching positive or negative infinity. Let me give you an example here. So if we had y equals to 3x squared plus 7 over like x plus 2, we would use that ratio for our end behavior model, our EBM. Okay, that ends up simplifying to 3x. Well, as x approaches infinity for our end behavior model, the y values would approach infinity. It's aligned with a positive slope. And as x approaches negative infinity, y would approach negative infinity. Okay, so because the y values are not approaching a number, there is no horizontal asymptote. Okay, there would actually be, in this case, the other type of end behavior asymptote that we're going to talk about, a slant asymptote, but there's no horizontal asymptote. Okay, so this is just in more words describing how you can locate horizontal asymptotes. All right, so let's look at these 3 examples here. So you can analyze the degree of the numerator and denominator, or we could also think about finding the end behavior model for the function. Right, in this case, we would have negative 3x to the 5th over 2x to the 5th, which simplifies to be negative 3 halves. So that tells us that f has a horizontal asymptote at y equals to negative 3 halves. This is not your answer. That's like your side work. The end behavior model is your side work. That doesn't tell me, you still need to tell me where the end behavior asymptote is, or the equation of the end behavior asymptote. Okay, so then let's look at the next one. So g of x, so ratio of the leading terms, our end behavior model will be 3x over 4x squared. So that simplifies to 3 over 4x. Okay, well, 3 over 4x is just 1 over x that has been stretched and compressed, right? Vertically stretched and horizontally compressed. And you know that 1 over x has a horizontal asymptote at y equals to 0. And that's because as x becomes infinitely large, and the same thing here, as x approaches infinity, y would approach 0. Same thing as x approaches negative infinity, y would approach 0. So we can say there is, so g has a horizontal asymptote at y equals to 0. And in this case, the degree of the numerator was less than the degree of the denominator. Okay, and behavior model. Simplifies to 3x. Okay, so 3x is aligned with a positive slope. So as x approaches infinity, y approaches infinity. We just had this, huh? And as x approaches negative infinity, y will approach negative infinity. So h actually has no horizontal asymptote. But h actually has a slant asymptote. And that's because looking at our end behavior model, notice our end behavior model is y equals to 3x, and 3x is a line. So H is actually going to have a slant asymptote at y equals to 3x plus something, right? Y equals mx plus b. We don't know what the b is. The end behavior model gives us what the slope of the line is going to be, right? That helps us to determine what the end behavior of the rational function is. It's just the slant asymptote is going to give us a better picture of what h is approaching, like how h is approaching positive and negative infinity. So we have to do some extra steps in order to find out what the exact equation of the slant asymptote is. So if f is a rational function where the degree of the numerator is exactly one more than the degree of the denominator, there's going to be a slant asymptote because your end behavior model is going to be aligned, just like in part C here. Okay, now if the degree of the numerator is, say, 2 more than the degree of the denominator, you're going to be able to come up with an end behavior model to determine what the end behavior would be, but it would actually be more like, in that case, a quadratic. So as x approaches positive and negative infinity, your function would be approaching either both ends positive infinity or both ends negative infinity. If it was 3 more, the degree were 3 more in the numerator than the denominator, the end behavior would be more like a cubic, and so on. But remember, asymptotes are lines. So I'm only going to ask you to come up with the end behavior asymptote. So if you can come up with a horizontal asymptote or a slant asymptote. In this specific case, where the degree of the numerator is exactly 1 more than the degree of the denominator. Now, if you were to do polynomial long division on your rational function, right, on n of x over d of x, you could rewrite your function in this form, right? So it would be m times x plus b plus r of x over d of x. Now, if there's no remainder, then you're just going to get mx plus b. Okay, now the degree of the remainder, r of x, is less than the degree of the denominator. We've talked about that before when we did polynomial long division. But the equation of your slant asymptote will be just the y equals to mx plus b. Okay, so let's determine the slant asymptote of this rational function. So if you think, like, if we didn't know this function had a slant asymptote and we were just given this rational function asked to find its end behavior asymptotes, we could think about finding our end behavior model. Okay, and we get y equals to x. Okay, well, y equals to x is a line. So this helps us determine what the end behavior is. Like, we know that as x approaches infinity, if we think about the end behavior model, y approaches infinity, so that means f of x will also approach infinity. And as x approaches negative infinity, because our end behavior model would approach negative infinity, so would f of x. But our end behavior model is not the equation of the slant asymptote. So we know that there's going to be a slant asymptote, but we need to do some work. So let's rewrite the function f of x, by doing some long division. So is that 5x, bring 2 down, plus 5, so we get 4. So f of x can actually be written as x plus 5 plus 4 over x minus 2. Okay, so that's f of x just written in a different form. Kind of like if you were to factor a polynomial, that's rewriting your polynomial function in a different form. This is just in a different form. Now, the x plus 5 is going to be the equation of our slant asymptote. So f has a slant asymptote. I'll just abbreviate actually with SA. Has a SA at y equals to x plus 5. So to kind of show you what that means, let me see if I can pull Desmos up here. Where's my Desmos? Okay, so I want to graph f of x. Oops. Y equals x squared plus 3x plus 2 divided by x minus 2. Okay, so that's what the rational function f of x looks like. And now let's graph y equals x plus 5. So y equals x, okay, plus 5. All right, so look, as we zoom out here, doesn't it look like the graph of f of x is kind of merging with the graph of y equals to x plus 5? Well, that's because as x approaches positive infinity, the values for f of x are going to approach positive infinity in the same way that y equals x plus 5 approaches positive infinity. Okay, same thing with as x approaches negative infinity, f of x will approach negative infinity in a similar way to y equals to x plus 5. That's why it looks like their graphs are merging together as we're zooming out. Kind of cool. All right, so we are going to look at graphing rational functions now. So we're going to follow these steps. So we'll state the domain of the function, locate any holes, find any asymptotes, so vertical asymptotes, and then also end behavior asymptotes. Right, this is for end behavior asymptotes. We can find any intercepts, and then it's sometimes helpful, well actually it's usually helpful, to find additional points near the asymptotes to figure out where like the branches of the graph will be. All right, so let's start with this guy. So in order to identify the domain, why don't we factor the denominator? Okay, so our domain looks like will be all real numbers except for positive and negative 1. Okay. We have no common factors that cancel, so there's no holes. But we do have vertical asymptotes at x equals negative 1 and x equals to positive 1. So I'm going to go ahead and sketch those. Please label them. I use a dashed line to draw the vertical asymptote. Okay. And then what do I say next? Oh, end behavior asymptote. So we could think about finding end behavior model. So 1 over x. So that means that as x approaches positive or negative infinity, our end behavior model will approach 0. So same thing with f of x. So that tells us that f of x has a horizontal asymptote at y equals to 0. The end behavior model is just like our side work. I'm going to sketch my horizontal asymptote. And label. Okay. So I believe intercepts are next. Should have used more contrasting colors. Yeah, so let's find our y-intercept. Our y-intercept and our x-intercept, it looks like, are going to be 0, 0. Okay. Actually, I'm going to use a different color for the actual graph so we can see. Okay, so it looks like we're going to need to find additional points because we do not know what is happening with this graph except for that one point. So let's deal with in between these vertical asymptotes first. So why don't we find f of 1/2 or f of 0.5 and f of negative 1/2. So 0.5 divided by 0.5 squared minus 1. Right, so I get negative 2/3. So 1/2 negative 2/3. Okay, so like down here. And then two-fifths. So negative 1/2 2/5. Is that right? Yeah. Okay, so this tells me, because the graph is going to approach, remember, the vertical asymptotes. It'll increase or decrease without bound as the graph approaches. So this tells me that it's probably going to approach like that. So then why don't we also find f of 2 and f of negative 2. Okay, so 2 divided by 4 minus 1. So 2 2/3. So that tells me that this is probably going to be approaching like this. And I think that it's probably going to be approaching y equals to 0 like that. And then for negative 2, remember these are like polynomials, these are just sketches. Okay, so we're having to do test points to really get an idea. With calculus, you'll be able to get more accurate graphs. Okay, so then negative 2/3, right? So it'll be kind of like that. Let's confirm let's confirm with Desmos. Let's see how close we were. Okay, so y equals x divided by x squared minus 1. Okay, not bad. Hey, look, they even did green. All right, not bad. Our graphs look pretty similar. Now we could also try and see like if our graph were to cross the horizontal asymptote at all by setting the function f of x equal to 0 and solving. Well, actually in that case we already do see it does cross, so we have that 1 point. Okay, let's look at the next one. Choose some better colors. Yeah, we'll go bright blue. All right, so why don't we first let's factor the numerator. So x squared minus 2x minus 3 over x plus 2. And then we can factor the numerator further. Minus 3x plus 1. Okay, so we can see that the domain is all real numbers except for -2. Okay, no holes again. Vertical asymptote at x equals -2. So I'll draw that. And behavior model. Okay, so we actually will not have an end behavior asymptote in this case because the end behavior of f of x will be similar to y equals to x squared, meaning as x approaches positive and negative infinity, f of x will end up approaching positive infinity, just like x squared. Okay, so the end behavior will be similar to x squared plus something. If we could get a better idea if we did rewrite f of x after doing polynomial long division, but we're not going to do that for now, unless we see like it seems like we need to. Okay, so x-intercepts are going to be wherever the numerator is equal to 0. So that's going to be at 0, 0. We'll have one at 3, 0, and -1, 0. I'm going to graph those. Okay. And y-intercept. So f of, oh, we have 0, 0, so it's going to be 0, 0. Okay. So we have to do some more points. This is kind of a tricky one. I'm not happy that I chose this one. All right, so let's figure out what's going on with, So let's find f of -3. So f of -3, there's just a lot of point plotting. Kind of wish I hadn't put this one on here. Oh, 36. That's way up off of my graph. Alright, what about f of -3/2? Okay, I got -6.75. Okay, so it's probably going to come down and decrease without bound. I don't know if this will cross. I think it probably will. But it does something like that. Think of that. Let's it's up here somewhere doing something like that. Let's graph this on Desmos. Just to see really how far we are off. Hey, it's not bad. Hey, that was actually pretty accurate. Okay. Yeah, not too bad. Although I would not give you one like this on a test where you have to really find so many test points to figure out what's going on with it. That was not very nice. Okay, so let's look at... there's a lot more. Alright, let's look at this guy. I don't know if I'll go through all of these. Maybe I'll make a separate video because this is getting kind of long. Alright, so let's first factor our numerator and denominator. What is this? Minus minus 2 minus 3 like that. Yeah. Okay. So no common factors. Jeez Louise, we haven't had one. Let's find one with a common factor. Let's look at this one. Nope, nope, this isn't going to either. There we go. Let's do this one. Okay, so our domain, let's write down our domain before we do any major canceling or major simplifying. So it'll be negative infinity to -3 union -3 to 2 union 2 to infinity. Okay, and then we have the common factor in the numerator and denominator. So this actually simplifies to just be x plus 1 over x plus 3. Let me just move that up. There we go. Okay, so there is going to be a whole at 2, and then we can find the y value by plugging into the simplified version of the equation. So is that 3/5? Okay, and there will be a vertical asymptote at x equals -3. Okay, end behavior model doesn't really matter if you take the simplified or the non-simplified version of the equation. You'd end up with the same end behavior model. So 1, right? So as x approaches positive or negative infinity, f of x is going to approach 1. Therefore, we will have a horizontal asymptote at y equals to 1. Excuse me. Okay, x-intercept at -1, 0, right, where the numerator would be equal to 0. And y-intercept at 0, 1/3. Okay, I have a feeling this is going to approach 1 as x approaches infinity like that, and that this will approach negative infinity. And then let me just find what f of -4 is. So that'll be -3 over -1, which is 3. Okay, so I think this will look like this. Oh, I forgot my hole. There's going to be a hole at 2, 3/5. So I think it'll look like that. So let's double check with our good friend Desmos. All right, it looks pretty good. Oh, they don't show the hole. Nope, they don't show the hole. But yeah, our graph looks pretty good. See, if we zoom out, the graph is approaching y equals to 1. Okay, and our vertical asymptote at x equals to -3. Okay, looks pretty good. I think what I'm going to do, because this video has already gotten way too long, I'll make another video of these last couple examples. So if you feel like you need more examples, then you'll have those to reference as well.